Okay, in this video we're going to do a couple of examples of integrals or problems involving integrals. So we'll start off with finding the integral of 3x squared minus 5x plus 1 over x, and then minus sine x, and then we're going to integrate with respect to x. There's your differential dx. If n is not negative 1, then the integral of x to the n dx is going to be x to the n plus 1 over n plus 1. So you add 1 to your exponent and you divide by your exponent, and then plus constant of integration. If n is equal to negative 1, then you have x to the negative 1 dx, which is the same thing as 1 over x dx. And that integral is the natural log of the absolute value of x plus c. And then the integral of negative sine of x dx is equal to the cosine of x plus c. Okay, so the first two terms in our integral, we're going to add 1 to the exponent and divide by that exponent. The integral of 1 over x is the natural log of the absolute value of x, and the integral of negative sine is positive cosine x plus constant of integration. We'll go ahead and reduce, and then that'll be it. Okay, so let's go ahead and look at another one. By the way, the numbering system was from the previous videos, which were doing derivative reviews. Okay, so we're going to look at the integral of the square root of x times x minus 1 dx. We don't really have right now a product, an antiderivative. This is what we're doing, finding antiderivatives. We don't really have a rule for products and antiderivatives. We have a product rule for derivatives, but we don't really have one for antiderivatives. So what we want to do is rewrite the square root of x as x to the 1/2 power, and then we'll go ahead and distribute that, and we'll use the power rule. So it's going to be x to the 1/2 times x, which is x to the 1/2 plus 1, which is x to the 3/2, and then minus x to the 1/2 dx. And then these are both power rules, so you're going to add 1 to the exponent, 5/2, divide by the exponent of 5/2. A minus, add 1 to the exponent, 3/2, divided by that new exponent of 3/2 plus c. And then flip over the fractions you're dividing by and change the operation into multiplication, and don't forget your constant of integration. Okay. All right. The next two examples are, we're going to be looking at a differential equation. We're going to be looking at the second derivatives equal to something, and then we're going to be given some particulars, and I'll get into that in just a second here. So we're going to find the s of t. That's going to be your position function. And then we're going to be given that the second derivative is equal to negative 32. And that number is going to be negative 32 feet per second squared. That's going to be your acceleration due to gravity. Okay. We are going to be given that the initial position is 2 feet, and the initial velocity is equal to 80. Why we're saying this is initial velocity, we can assume that in this context that t is going to represent time, probably in seconds, because the acceleration is in feet per second squared, and so yes, the t would need to be seconds. So initially, because t is equal to 0 there. So we have the particular velocity and the particular position, so we can get a particular solution for this differential equation. If we are unable to, if we don't have initial conditions, then we'd have a general solution. So let's go ahead and write some stuff down. So s of t, that's going to be your position or height at time t. S prime of t is going to be a v of t, which is your velocity, so your velocity at time t. And then your second derivative, s double prime of t, is equal to the first derivative of velocity, and that is going to be your ace of t, or your acceleration. So the scenario, maybe we're shooting off a rocket or something from 2 feet off the ground. We know that the initial speed is 80 feet per second. and we know what the acceleration due to gravity is, so we could come up with a position function that would model the height of the rocket at various points in time. If we wanted to, we could figure out what the maximum height is and so forth. Okay, so to find the velocity, we need to integrate the acceleration. Okay, so to find s prime of t, we need to find the antiderivative of s double prime of t, or integrate s double prime of t, which is negative 32 dt. So the integral of a constant is that constant times t plus a constant of integration. So that's going to be negative 32t plus a constant of integration. Now you're going to use your initial velocity to actually find what particular c we're interested in. So this is going to give us what c is. So s prime of 0, we're going to go ahead and plug that in. It's going to be negative 32 times 0 plus the constant of integration c. And the initial velocity was equal to 80. Well, that's just going to tell us that c is equal to 80. And so we now have our velocity function of negative 32t plus 80. And so this will tell us what the velocity is, for example, of our rocket at various points in time. All right. Now, if we want to find the position, we'd have to find the integral of the velocity, or the antiderivative of the velocity, which is s prime of t. So we're going to find the antiderivative of negative 32t plus 80 dt. So it's going to be negative 16t squared plus 80t. And then we get a new constant of integration. Then we'll use our particular condition that the initial height was 2. So s of 0, I'm going to go ahead and plug in 0 in for t. And then the plus the c, and that's going to be equal to 2. Now everything's going to zero out except for the c, so this is going to give us c is equal to 2. And so now we have our particular solution here. This is our position function that meets this criteria. So again, if you wanted to use this to figure out what the height is at a certain point in time, you can. You can also find the maximum height using this function. Okay, we're going to go ahead and do one more of these. Whoops, what happened? And if you're following along the notes, this was, I don't think I numbered it, this was number 13. We're going to do another one like this. It may not have a story attached to it, but it is similar. So we're going to find the original function f of x, given that the second derivative is 6x plus 6, and then we're going to be given particular conditions that f prime of negative 1 is 4, and f of negative 1 is equal to 5. So we're given those particular conditions, so we're going to solve this differential equation here. So we're just finding what f of x is. Okay, so f prime of x is equal to the antiderivative, or the integral, of f double prime of x dx. So we're going to integrate the second derivative. And when we integrate that, that's going to give us 3x squared plus 6x, and we get a constant of integration. Use your particular that was given to you, f prime of negative 1 is equal to 4. Okay, so we're going to replace the x with negative 1. And then this is going to be equal to 4. That's what they told us it was equal to. Okay, so we'll simplify that down. Negative 3 plus c is equal to 4. So then c is equal to 7. And so that gives us a particular first derivative, 3x squared plus 6x and plus 7. And so to get from the first derivative to the original function, you're just going to take the antiderivative, or you can integrate the first derivative. So we're going to integrate the first derivative. So the integral of 3x squared plus 6x plus 7 dx. Okay, so that's going to give us x cubed plus 3x squared plus 7x, and then plus constant of integration. Use your particular condition given, f of negative 1 is equal to 5. So plug in negative 1 for the x's. And that's going to be equal to 5. Okay, and that's what the particular condition was given. Okay, we'll go ahead and simplify this down. So negative 5 plus c is equal to 5. So this tells us that c is equal to 10. And so our particular position here, oh, I am calling it position, hold on a second. It could be a position, but it was f of x here, so hold on a second. This should be f of x, okay? Alright, so f of x is equal to x cubed plus 3x squared plus 7x plus 10. Okay. I think I have one or two more videos with a little bit of review of integrals. So we'll see you next time.